today to continue with the plant water relationship. Okay, see, yesterday I was discussing about the transport in plants. Okay, now we are going to see in the transport in plants, the next relationship is how does the plant water relationship is going to happen. Okay, to conclude this plant water relationship, there are a lot of theories have been applied. The first one, before going into that, as you all know that water is the essential for many things in the plants. Okay, 85 to 90% of water is required for the transportation in plants. Okay, in that, if you take that water which is present in the soil, we called it as either capillary water or gravitational water or hygroscopic water. The water can be water which is present in soil, we called it as capillary water, gravitational water, or hygroscopic water. So based on this theory, we have come to a conclusion of first one is osmotic or solute potential. Osmotic or solute potential. You must be knowing that osmotic pressure is completely different from the osmotic potential. Here in osmotic or solute potential, osmotic potential decrease in chemical potential of pure water due to the presence of solute present particles in it. Say for example, when you take a pure water, okay, in that pure water, the chemical potential, the presence of chemical potential determines the osmotic potential. Usually, the osmotic pressure will be having a positive sign, whereas osmotic potential will be having a negative sign. So remember that in osmotic potential, osmotic pressure will be having positive sign, whereas osmotic potential will be having negative sign. So to determine that osmotic potential in the osmotic pressure, we have come to a formula which determines osmotic potential equal C into R into T. Now you must be wondering, what is that C, R and T denotes here? Okay, here this osmotic potential, this denotes the osmotic potential, and C denotes the concentration of solute present in the particles. So imagine if you take a, I'm just giving you an example. Okay, if you take a water, okay, in that bowl of water, the concentration of solute particles present in it will be determines that. Next is the R. R determines the gas constant. Usually in a water, the gas constant will be 0.083%. Okay, next coming to the temperature. That temperature determines the major factor in the osmotic potential. So to write out this osmotic potential formula, it is C into R into T. So this will be osmotic potential formula. Now, as I've already told you that osmotic potential is negative sign, whereas osmotic pressure is positive sign. So, when you take an osmotic potential in water, it will be 0 degree centigrade. Okay. So, because of that negative sign, what happened is the water diffused from colder liquid to the warmer liquid. So, because of that negative sign alone, the water is transferred from the colder part to the warmer part. So, usually warmer solution has more negative osmotic potential than the colder solution. So, this is about the osmotic or solute potential. Next, we move on to Turgor pressure. Turgor pressure. In simple, we write it as TP. In simple word, we write it as TP. Turgor pressure. What is an Turgor pressure? As I've already told you about the end osmosis, right? In end osmosis, when you keep a flaccid cell into the hypertonic solution, the water enters into that flaccid cells and the cell becomes turgid, right? That's exactly will be happening in the end osmosis. So, while entering that kind of a water into a cell will leads to a pressure. That pressure we called it as Turgor pressure. In simple terms, if you keep a plant cell into a hypotonic solution, then water enters into the cell sac by end osmosis. This is a normal procedure which is happening in the end osmosis. So after this normal procedure happening in the end osmosis, that leads to a pressure. So that pressure we called it as Turgor pressure. So you must be knowing the definition for Turgor pressure. So next to the Turgor pressure, so that Turgor pressure, what happens is if it is continuously given a Turgor pressure, that Turgor pressure presses the protoplast against the cell wall and cell becomes turgid. So this Turgor pressure presses protoplast against cell wall and the cell becomes turgid. So once the Turgor pressure develops, that pressure will be pressing out the protoplast against the cell wall. That is how the cell becomes turgid. Okay, all this we called it as Turgor pressure. Turgor pressure can also be called it as hydrostatic pressure. Turgor pressure can also be called it as hydrostatic pressure. Now, you must be wondering, see, without a pressure, any reaction may not be happening. So, with that hydrostatic pressure or Turgor pressure, that, that creates the wall pressure. Usually, Turgor pressure alone will create the wall pressure in the cell wall. Why the cell wall has to create a pressure? You must be wondering. So, this wall pressure, when the Turgor pressure creates the wall pressure, that leads to the protoplast to detach from the cell wall. So, consequence of Turgor pressure which leads to wall pressure is created. Now, TP is equal to WP. Here the TP stands for Turgor pressure which is equal to the wall pressure. So, this is about the Turgor pressure. The third one we are going to discuss about in plant water relation is metric potential. So, to say the metric potential, this is the simple term which is used to denote the metric potential. Metric potential is not so important when we talk about the plant water relation, because the expression of absorption of water by colloidal particles. I think I have already told you about the imbibition, right? In imbibition, it is the absorption of water by the solid particles. That's exactly is happening in the metric potential. It is the expression of absorption of water by colloidal particles. Colloidal particles is nothing but it is the solid particles. So, it is not so important in the plant water relation when compared to the osmotic potential and Turgor potential. The fourth one is chemical potential. The chemical potential, the word itself clearly says. So, whenever there is any chemical which is present in the water, which determines the chemical potential. So, it is chemical potential is a quantitative expression of free energy associated with per mole of any chemical in a system. So, this chemical potential purely produced based on the amount of chemical which is present in the water. So that we say it, that was explained in this point. And free energy is, as you know, that chemical potential will carry the free energy. So if the larger chemical potential of a substance, which leads to the greater the tendency of undergo to chemical reaction. If the chemical potential determines how much amount of chemical which is present in the solvent determines the chemical reaction. So usually, as you all know, that for osmotic potential I have given you the formula, and Turgor potential I have given you the formula, and metric potential I have given. That's exactly, it's applicable for the chemical potential also. So here the per mole of substance unit of chemical potential is determined by J mole minus 1. This determines the chemical potential. So if you take from this plant water relationship, these potentials are important. Okay, so in that, the first and foremost important of the plant water relation is osmotic or solute potential. This is very important. When it comes for the formula C minus R minus T, that is again important. Next is the Turgor pressure, because without Turgor pressure, endosmosis, it is not possible. So that for that end, Turgor pressure is important. And this metric potential and chemical potential, it determines how much amount the substances present in the solvent, which determines their potential. When you talk about overall about the plant water relationship, this two, osmotic potential and Turgor pressure potential, is very important point. Okay.